Hello from the Netherlands. I'm Sagar Adatrao from Delft University of Technology. I will take you through the concept of design of experiments and its application to PIV uncertainty quantification. This work was done in collaboration with Royal Netherlands Aerospace Centre, in short NLR, and the German Dutch wind tunnels, in short DNW, here in the Netherlands. The work was funded by the Netherlands Research Organization NWO. I would like to start with a basic question. Do we know the uncertainty in PIV experiment completely? Think for a while and let me know your answer. I was asked the same question by many PIV experimentalists like you. One of them was Simona, a student at the Royal Netherlands Aerospace Centre NLR, who planned to perform stereoscopic PIV measurements for the flow at the outlet of a ducted boundary layer ingesting propulsor at German Dutch wind tunnels. She and her team came up with some more questions. What should be the levels of the experimental factors like f-stop, delta t, interrogation window, stereoscopic angle alpha? Can we know the systematic uncertainties due to these factors and their interaction, along with the total uncertainty? What do you think? Can we answer all these questions in a single measurement campaign with limited time and resources? I said yes, and introduced design of experiments to them. What is DOE? DOE is a process of planning the experiment in order to collect appropriate data, which we can analyze by statistical methods to come up with valid and objective conclusions. Let's compare it with the conventional way of measurements, that is one factor at a time, OFAT. In OFAT, as the name suggests, we change the level of one factor at a time, keeping the levels of other factors constant. On the other hand, DOE is based on the principle of changing the levels of multiple factors at a time. This leads to the reduction in the total number of runs or data points for DOE. The conclusions are presented in OFAT in the form of plots. For example, for wind tunnel test, to know the effect of angle of attack on lift or lift coefficient, we need to plot such a plot for each Mach number separately. On the contrary, in DOE, the conclusions are drawn with the help of single ANOVA table. Overall, DOE is more advantageous than OFAT since it is more efficient, that is, small data volume. The conclusions can be drawn on wider range of the factor levels, and the interaction of two or more factors can be computed. However, how to quantify the uncertainty using DOE? It is quite simple, as shown here for the experiment with two factors. The analysis of variances, that is ANOVA table, gives us the variances in the output due to the individual factors and their interaction, along with the total variance. These variances lead to the computation of the related systematic uncertainty and total uncertainty. For detailed explanation, please check out the paper. Now let's come back to the experiment of NLR and their requirement of uncertainty quantification. I propose them to consider f-stop, delta t and interrogation window size as design factors and the stereoscopic angle as a blocking factor. The main difference between the design and blocking factors is that the levels of the design factors are changed randomly, whereas the levels of the blocking factor are constant. In other words, the measurements are carried out in different blocks where each block corresponds to the level of the blocking factor, and the levels of the design factors are varied randomly in each block measurements. The stereoscopic angle was chosen to be the block since it is not feasible to change the camera angle after every measurement. Two levels were considered for all the factors, low and high, which resulted into 8 runs per block, that is 2 to the power 3. Here k is the number of design factors and 2 the number of levels of the design factors. Let's see how the results look like. The estimated time average streamwise velocity component u and in-plane velocity vectors are shown in the left figure. On the right side, you can see the contour plot of the total uncertainty in the time average streamwise velocity u. In the velocity field, wake region can be seen in the center, whereas the outer region represents the potential flow. The flow is retarded at the periphery of the propulsor, and the discontinuities in the mean streamwise velocity field due to the stator ring can be seen at the periphery. Moreover, the in-plane velocity vectors here represent the magnitude and direction of y and z velocity components v and w respectively. The counterclockwise rotation of the flow in the wake of the propulsor can be easily seen due to the direction of the vectors, where the magnitudes of v and w velocity components are larger than those in the outer potential flow region. The contour plot of the total uncertainty shows that the uncertainty is higher at the outer edge of propulsor slipstream, which is characterized by high flow fluctuations and high velocity gradient. Thus, the total uncertainty is proportional to the amount of flow fluctuations and local in-plane velocity gradients as expected. To show the detailed results of systematic uncertainties, 4 regions are selected based on the amount of flow fluctuations and velocity gradient. The figures here show the magnitudes of local in-plane velocity gradient for streamwise velocity at the top and RMS of fluctuations in the streamwise velocity normalized by the free stream velocity at the bottom. The 4 regions of analysis are shown by the red squares. The systematic uncertainties due to the individual factors are calculated by following analysis of variances. Their contributions to the total uncertainty in the streamwise velocity are shown in the form of pie charts for the 4 regions. The corresponding total uncertainties in the mean streamwise velocity can be seen at the centers of the pie charts. As mentioned earlier, the total uncertainty increases with increase in the velocity gradient and the flow fluctuations. The analysis shows that in most of the measurement domain, the main effects of the factors f-stop, delta t and stereoscopic camera angle alpha are statistically significant, whereas the main effect of interrogation window size di and all the two-way interaction effects are found to be insignificant. The blocking factor alpha is the most significant factor in all the 4 regions. It is due to the slight misalignment of the 2 measurement planes of the 2 blocks of measurement. However, this uncertainty corresponding to the stereoscopic angle can be easily reduced by implementing a proper self-calibration, which was not applied in this study. The factor delta t corresponds to the out-of-plane motion of the particles, and it has significant contribution to the total uncertainty in the regions of high velocity gradient and or high fluctuations, that is regions 2, 3 and 4. Moreover, for the regions of high flow fluctuations, that is regions 2 and 4, the random error has the biggest contribution to the total uncertainty. This is due to the flow fluctuations in these regions being high makes it difficult to segregate the contribution of individual systematic uncertainties. It is to be noted that the error uncertainty represents the random uncertainty in measurements plus the uncertainty due to the unknown experimental factors, that is the factors not considered as design or blocking factors. Now let me summarize the work here with some bullet points. First of all, I am happy that PIV experimentalists received answers to their questions. They successfully applied design of experiments to calculate the systematic uncertainties arising from the different experimental factors. And it was possible in limited amount of time in a single measurement campaign. It will also be possible for them to optimize the experiment to reduce the uncertainties based on the results of the analysis. Lastly, I would like to say that the proposed methodology can be applied for uncertainty quantification not only for the time average velocity, but also for the higher order statistics like Reynolds stresses. The approach can also easily be implemented to 3D measurements. If you have any questions or comments, please let me know via an email. Of course, I will be happy to discuss them also during the question and answer session of the conference. Thanks for watching.